Hi everyone. Today we're going to look at something called geometric sequences and series. The geometric sequences series are very relatable to exponential functions, and that's why it's at the end of this chapter. Okay, in the first part of this lesson, we're going to talk mainly about geometric sequences, and we're going to be able to write geometric sequences in two different forms. So let's begin. So this is a nice comic I've seen before. Okay, half off haircuts, where the animal gets half of his hair cut off, and then half of his hair cut off, and half of his hair cut off. And it's a sequence where there's constantly half the hair there was before. It's an okay joke. So today we're going to deal with, like I said, geometric sequences. We're going to learn about recursive form and explicit form. We're going to use those to create equations and then solve the equation, solve problems with the equations. So let's start with this problem. So a store offered customers two plans for getting bonus points. You can get 10 points today and get double the amount of points every day from now on, or you can start with 1 point and get triple the amount of points. So your job is to tell me on the 7th day which plan gets me the most bonus points. So go ahead, pause the video, try it out, write equations that represent the situations, and then tell me which plan is best. Okay, so hopefully you saw that we have a starting value and a multiplier for each case. So for plan A, I start with 10 and then I double. So my multiplier is 2. And then for B, I start with 1 point and then my multiplier is 3. They're both functions of time. And the question really asks, on the 7th day, which one's better? So if I put 7 in for T in both of them, I see that plan B is better, just on day 7. And if you look further out, B is going to be increasing faster because it's tripling compared to A, which is doubling. So the beginning A was better, and then the end B is better. And these are situations we have to look at in the real world. Sometimes a situation is better at first, but not better at the end. And this is what we're going to be looking at. This is going to lead into geometric sequences. So a geometric sequence is a sequence, it's a list of terms where there's a common multiplier, a constant ratio between each term. Okay, and the ratio is called R. So in the last problem, we had a ratio of 3 or a ratio of 2, depending on whether you chose option A or B. So we're going to start with an idea called a recursive formula. So recursive formula is very useful, especially in computer programming, where it takes a term, we do something to that term, and we get the next term. And then we repeat the process over and over again. So in order to write a recursive formula, we need to know the first term, or really any term. We generally use the first term. And then we tell it to get to the next term, what do we do? So this is the formula. I'm going to explain more of this momentarily. And you're also going to see me use the letter G instead of A for geometric. A we generally tend to use for something else. So let's look at an example, and we're going to create one together, and you're going to see how we go about this. So is the sequence here geometric? If so, we got to write a recursive definition. So I look at the terms to see 4, 12, 36, 108, and 324. And I check, do I know how to get from 4 to 12? Now, if I do, great. If I know the multiplier and I do right now, it's 3. But if not, I could take the second term and divide it by the first. and I could take the third term and divide it by the second. So on, check to make sure that the ratio is constant amongst all of them. So I know my common ratio is 3, and I know my first term is 4. Now, in this way, I can write a recursive definition. I can say, well, to get to the next term, so we'll call g of n the next term, we take the previous term, which is the n minus 1 term, and multiply it by 3. And then we got to tell the user, which is us in this case, okay, we can start our first term is 4. Now we need these two parts. Now the book might write it a little bit differently, and we're going to see how they write it. But at the same time, we need to understand, you need to be able to tell us to get from one term to the next term, we need our multiplier, and where our starting term is. Generally, we start at the first term, although you can start at the second term, the third term, any other term you want. So what they did here, they found the multiplier. Okay, they said the multiplier gets us from A1 to A2, and A2 to A3, and A3 to A4. We start with 4 as the first term. So the way they wrote it is this. So they said the first term, n equals 1, is 4. And you do 3 times the last term to get to the next term. Both ways work. I tend to write it in a shorthand. This is called a piecewise function notation, and it works as well. So let's take a look at another one. Is this a geometric sequence? And if you're feeling really bold, you can pause the video and try it out. If not, here's the answer. So for this case, I don't know that 12 times 0.8 is 9.6. So once again, do new divided by old. So 9.6 divided by 12 and 0.68 divided 7.68 divided by 9.6 and 6.144 divided by 7.68. And each time the multiplier is 0.8. So in this case, we start at 12, and each term we multiply by 0.8 to get the new term. The way I would have written this, I would have said g of n equals 0.8 times g of n minus 1, and g of 1 equals 12. Both notations are fine. We generally assume that n has to be positive and n has to be an integer because we can have term 1 or term 2 or term 3. There's nothing between term 1 and term 2. So this is what a geometric sequence looks like in recursive form. Now it's your turn to try a few. So you got two sequences here. Tell yourself, is it geometric? If it is, write a recursive definition. Pause the video, try it out. When you're ready, we will continue looking. Okay, so you tried it out. Let's see how you did. So this first one goes up by constant addition, so not multiplication. There's not a constant ratio. This one's called algebraic. It's an algebraic sequence, and we can write a recursive definition for it. Okay, we could say, hey, from the last term to the next term, you add 0.23, and you start at 1.22. But we don't need to be focused on that. The question asks only if it's a geometric sequence, then we write the recursive. So this right one definitely is. You multiply by negative 1/2. Okay, the first term is negative 1.5, so I write it like this. To get from one term to the next term, you multiply by negative 0.5, and the first term is negative 1.5. Now the book will probably have you write it like this. Okay, it says you start at negative 1.5 when n is 1, and when n is bigger than 1, you have negative 0.5 times the last term, g of n minus 1. And both forms are okay, once again. As long as you know the multiplier and the starting term, you can write the recursive form. And I actually think that's the more challenging of the two forms. The second form is the explicit. Now, the explicit form looks very much like an exponential function. The difference between a function and a sequence is discrete, so n has to be an integer. So n has to be a whole positive number. Once again, we need the first term and the common ratio. So think of it as starting value in your multiplier again. And n minus 1 just means we shift 1 to the right. We start at the first term here because we don't really ever have a zero term. So let's take a look at how to write an explicit definition. And we're going to go back and forth between recursive and explicit depending on what the problem asks, depending on how we need to use it. So it gives us a recursive definition here. Our starting term, our first term is 5, and our multiplier is 1/2. So we need to write the explicit definition. So we need to say that to find any term, you need to start at 5, and you multiply it by 1/2, however many times we need. And I could check that this works. Okay, I know that if 5 is the first term, going by half every time, 2.5 needs to be my second term. So I can test it out and say, hey, g of 2, does that get me 2.5? So you have 2 minus 1 is 1, 1/2 to the first is 1/2, and half of 5 is 2.5. So this is my explicit definition, which is very similar to the formulas that we've come up with for many years. So once again, here the book wrote the same thing. They showed it out as, okay, these are the ratios. So R is 1/2, 5 is our starting term. Okay, still the n minus 1. Okay, the exponent's going to be n minus 1 as long as this is the first term. Now we can also go backwards. We can start an explicit and go to recursive. So once again, it's the same idea where we take the pieces of information. So I see my first term here is 3. And I see my ratio, my common ratio is 2. So I can write it, and I'll write it in the way the book likes it. Okay, we say 3 when n is 1. And then when n is greater than 1, we take 2 times the last term. Okay, so recursive is kind of like a set of instructions where you tell them where to start and what to do to get to the next term. And they wrote it exactly how I wrote it. They don't put the curvy brace around the end. I'm not sure why. But this tells us start at 3, multiply by 2. So it would be 3, then 6, then 12, then 24. That would be my geometric sequence. And sometimes it helps to write out a bunch of terms to see, is it doing what I want it to do? So now you go for it. Take the explicit, make it recursive. Take the recursive, make it explicit. Pause the video when you are ready. We'll take a look at the answers. Okay, hopefully you got 2 out of 2. Okay, I didn't get 2 out of 2 because that should say 1/3. 1/3, much better. And the second one, okay, once again, we need 2 details. We need the first term is 6 and the multiplier is 1/2 to get from the last term to the first term. Okay, and now we can write explicit or recursive, and depending on what we need is which form we're going to use. And that gets us into solving. So way back when, before the internet, there used to be something called phone trees. They still kind of exist, but not as much. So one person calls a number of people, then those people call the same number of people, and so on and so on and so on. Okay, so it looks here like we have 1 and my multiplier is 3. So one person calls 3 and each one of those 3 calls 3. Okay, so my explicit equation is 3 times 3 to the n minus 1. Okay, we're really going to say this is the first round is these 3 people. So now the 8th round, we put in 8, and we can find out how many people were called after the 8th round. And really big companies need to know this to know how many different levels do I need to make. Okay, so if they have 6,000 people in the company, they need 8 rounds. So we can come up with an explicit formula. Then we can come up with how many after any round. This form I like a little bit more than recursive, because recursive, you need to find the first round, then the second round, then the third round, then the fourth round, then the fifth round. And it just seems cumbersome. So now I want you to try it. Okay, and this one is a nice challenge for us because you got to find the starting value and the multiplier, and you got to come up with a sequence, and you got to figure out how many bacteria are in the dish on the 7th day. So pause the video, take your time, figure this out, and then we'll go through it step by step after you have your answer. Okay, so hopefully you took a lot of thinking and time to do it. You got it right. If you didn't, we'll see where you made a mistake. So it tells me my first term is 9, and I'm going to write it as 3 squared because on day 10 they tell us as 3 to the 20th. Can still be done if you don't write it as 3 squared, but you're going to see why 3 squared is useful in a minute. So 3 squared, my starting value, times r to the 9th, because I'm taking 9 steps to go from day 1 to day 10, is 3 to the 20th. And now I got to solve this for r. So this, I think, was the hardest part of this problem. Now I got to use some exponent rules. I can divide both sides by 3 squared, and then I can take the 9th root, and I get down to r equals 9. If you don't remember how to do that, we can talk about it. But we got to remember solve algebraically. We can use exponent rules. When do we subtract? When do we divide? So now I have an explicit equation. I start with 9. My multiplier is also 9. That just is coincidence, to the n minus 1. And then it wants me to substitute 7 in to figure out how many bacteria there are on day 7. And I could do that. And I get 4,782,969 bacteria. So this is how we use geometric sequences. Okay, we can use this to extrapolate data or figure out how many bacteria there are at each point or each day. And this is our introduction to geometric sequences. Now we know how to write explicit equations and recursive equations.